Here's a problem that looks harmless and then blows up. You're tracking a few yes or no facts about a house at night: a burglary, an earthquake, the alarm, and two neighbors who might phone. Five true or false variables. To answer any question about them, you'd want the full joint distribution, a probability for every combination. And that's the trap. Five binary variables give 2 to the fifth combinations, 32 rows. The probabilities must sum to 1, so you're free to pick 31 of them. 31 numbers for a tiny toy problem. Now imagine not 5 variables but 50. 2. The 50 is a 16-digit number. More rows than you could ever write down, let alone estimate. The full joint table is a dead end. A Bayesian network is the escape. It exploits a simple truth. Most variables don't influence most others directly. Draw only the influences that matter, and the 31 numbers collapse to just 10. Here is the whole idea in one picture. Every variable becomes a node, a circle. Burglary and earthquake up top, the alarm in the middle, and the two neighbors, John and Mary, at the bottom. Now the arrows, the heart of it. An arrow from X to Y means X directly influences Y. A burglary can set off the alarm, so we draw an arrow from burglary to alarm. An earthquake can too, and the alarm is what the neighbors actually hear. So the alarm drives John's call and Maria's call. Two arrows down from the middle. Notice what's missing. There's no arrow straight from burglary to John. A burglar doesn't phone your neighbor. John only reacts to the alarm. Those absent arrows are where the savings come from. One rule keeps this honest. The arrows can never form a loop. That makes it a directed acyclic graph, a DAG. Follow the arrows and you always move forward, never in a circle. The graph tells you who influences whom, but we still need real numbers. So every node carries a small conditional probability table, a CPT, giving the chance of that node's value for each combination of its parents. Start at the top. Burglary has no parents, so its table is just a plain prior, a rare 1 in 1,000 chance. Earthquake, likewise, 2 in 1,000. Now the alarm, the interesting one. Two parents, so its table needs a row for every combination. 4 rows. With both events, it almost surely fires, 95%. With neither, it's essentially silent, 1 in 1,000. And the two neighbors, each has one parent, the alarm. So each table has 2 rows. If the alarm rings, John calls 90% of the time, Mary 70. And even in silence, they occasionally call by mistake. One quiet rule governs every table. Fix the parents. Burglary, yes. Earthquake, no. And the alarm's chances must sum to 1 across its own values. 94% it rings. 6 it doesn't. That holds in every row on its own. You never add across different rows. Here is the payoff that makes the whole structure worth it. The full joint distribution, the chance of any complete scenario, is just the product of every node's table, each conditioned only on its parents. For our alarm network, that's exactly 5 factors, 1 per node. Burglary and earthquake stand alone. The alarm given both, and each call given only the alarm. Why is that allowed? The exact chain rule writes the joint as a chain of conditionals, each variable depending on all the ones before. Look at the last term, Mary, conditioned on all 4 others, but the graph says Mary only listens to the alarm. Once you know the alarm state, everything else adds nothing. So that monstrous term collapses to Mary given the alarm alone. That's the golden rule. Every node is independent of its non-descendants, given its parents. Apply it to each chain rule term, and it shrinks to the tidy product. 1 factor per node, parents only. Let's compute one. Tonight, both neighbors called, and the alarm fired. But there was no burglary and no earthquake. A pure false alarm. What's the probability of that exact scenario? The factorization hands us the recipe. It's the product of 5 table entries. No burglary, no quake. The alarm firing given both absent. Then John and Mary each calling given the alarm. Now read one row out of each table. No burglary is 0.999. No quake, 0.998. The alarm with neither cause is that tiny 0.001. John given alarm, 0.9. point 0.9. Mary given alarm, 0.7. point 0.7. Multiply them through. The two priors give about 0.97. The tiny alarm term drops it near 0.001, and the two calls bring it to roughly 0.00063. A tiny number, and it should be. A night where the alarm shrieks for no reason and both neighbors ring is genuinely rare. Pick one row from each table and multiply. That's the whole workflow. Let's do a second, at the other extreme. The most ordinary night imaginable. No burglary, no earthquake, no alarm, neither neighbor calling. How likely is that? Same recipe, 5 factors. But now every value is the negative one. So we read the complements. The alarm staying silent, and each neighbor not calling. Plug in the numbers. 99 in, 99 it. Then 99 in again for the silent alarm. Then 0.95 and 0.9 in for the two quiet neighbors. And that comes to about 94%. Exactly right. On most nights, nothing happens. So this one peaceful scenario soaks up almost all the probability. So how much did the graph buy us? Let's count the numbers you must store. The naive full joint on the left, the network on the right. The full joint stores one number per row. -1 because they sum to 1. 31 numbers, as we saw at the start. Every one estimated from data. Now the network. Each node stores one number per row, and the rows are 2 to the power of its parent count. Burglary and earthquake, 1 each. The alarm, 2 parents, 2 squared, 4. John and Mary, 2 apiece. Add them up. 1 plus 1 plus 4 plus 2 plus 2 is 10. 31 numbers become 10, and the gap only widens as the network grows. That is the whole reason Bayesian networks exist. Something remarkable is hiding in the graph. You can read which variables are independent straight off its shape. 3 little patterns cover almost everything. First, a chain. Burglary to alarm to John. Information flows along it, but block the middle. Given the alarm, John becomes independent of the burglary. The alarm was the only channel between them. Second, a fork. One alarm feeding both John and Mary. On their own, the calls look linked, since both point back to the same alarm. But fix that common cause, and the link vanishes. Given the alarm, John and Mary are independent. Third, and this one genuinely surprises people, a collider. 2 arrows crash into the alarm. With nothing observed, burglary and earthquake are completely independent. A break-in tells you nothing about tectonic plates, but now condition on the alarm. Suddenly they're linked. The alarm is blaring, so something set it off. And if you learn an earthquake struck, that explains it, and the chance of a burglary drops. 2 causes competing for one effect. That effect has a name, explaining away. Chain and fork open up when you condition. A collider does the exact opposite, coupling what was independent. Your turn, and this one you can fully solve. Same network, same tables. Find the probability of this scenario. No burglary, no earthquake, and yet the alarm fired, and both John and Mary called. A false alarm that fooled everyone. Here's the walkthrough. The factorization is the same 5 factors as before. The 2 absent causes, the alarm given both absent, and each call given the alarm. Read the rows. No burglary, 999. No quake, 998. The alarm firing with neither cause is that same tiny 0.001. Then John, 0.9, and Mary, 0.7. And that's the very same product from the first example. about 0.00063. If you set up those 5 factors and got 6.3 times 10 to the minus 4, you've genuinely understood the method. Trap 1. Conditioning on ancestors instead of parents. Maria's factor is Mary given the alarm, not given the alarm, and the burglary, and the quake. Drag in grandparents, and you lose the whole saving. Trap 2. Normalizing the wrong way. Probabilities sum to 1 within a single row for one fixed setting of the parents. Never add down a column across different parent combinations. Trap 3. Forgetting the collider. Two causes with a shared effect are independent until you observe that effect. Then explaining away kicks in. It catches almost everyone. And trap 4. Reading every arrow as hard proof of cause. Arrows encode which variables depend on which. They often match causation, but the graph alone doesn't prove it. Let's lock it in. A Bayesian network is two things: a directed acyclic graph showing who influences whom, and a small conditional probability table on every node. Together, they factorize the entire joint into a product of local terms, each node conditioned only on its parents. That's the one equation to carry away. And the payoff is enormous. 5 variables, 31 numbers become 10, and the gap explodes in your favor as the problem grows. As a bonus, the graph reveals independence, chains and forks that open when you condition, colliders that surprise you by coupling. Draw the arrows, fill the tables, multiply, and the impossible becomes 10 small numbers.